Trusses are special structures comprised of only axial members. A truss is a structure composed of slender members which carry only axial loads, joined together at their endpoints. The joints between members can't carry moment, and you'll hear me often talk about a truss having joints or hinges. So here's an awesome Lego door, and you'll see that when you open it, it has a hinge. What's special about a hinge? A hinge is a connection that can carry forces, so I can pull on the door, I can push straight into the door, and it doesn't move. But when I apply a force perpendicular to the hinges, it rotates. So the joints of a truss are hinges. They can't resist moment, and they can rotate freely. Again, members can carry only axial force, but that force can be in tension or compression, and truss behavior can only be achieved when point loads are applied to the joints. So here I have a nice simple truss. If I apply a force in the middle of a truss member, I will not have pure truss behavior. There will be some bending. That is not a truss. If I want to have truss behavior, I can only apply forces at the joints. And you'll notice that the reactions and the supports are also located at the joints. Now, a truss is a structure, and here in statics, we only have, as our only tools are our equations of equilibrium and section cuts. So that only gives us the ability to analyze determinate structures. And a determinate structure is the state where the unknown forces equal the number of equilibrium equations. Now, in order to do this, I've created a simple rule of thumb equation. It's not perfect, which we'll get to in a second, but it will get you pretty far. I, for indeterminate, is equal to m, which is the number of members, plus r is the number of reactions, minus 2j, where j is the number of joints. Now, m plus r gives us our unknown forces. Two plus j gives us how many equations of equilibrium we can write. And we can write 2 for each joint. Now, you might say to yourself, why do I only get to write 2 equations at each joint when I have 3 equations of equilibrium? The answer to that is pretty simple. Since if I look at a random joint anywhere, you'll see that there are multiple members that can tie into it. It can be 3 members. But all these members tie into a joint, and this joint is a hinge, so it can freely rotate it. I can sum forces in the x, I can sum forces in the y, but if I try to sum the moment at the joint, we find that all the forces act through that joint so that there is no moment. So our sum of the moments will always be 0 and is trivial and useless. Now, so for each joint, we get 2 equations of equilibrium. If this equation, I, turns out to be 0, we have a determinate structure, and we are good. If I is greater than 0, it's indeterminate. And we can't solve, at least yet. We need some more advanced techniques to be able to solve that. If it turns out to be less than 0, you have something that's called unstable. And that is no good. That's when you have less forces than equations of equilibrium. Now, if I were going to come down here and solve or determine if this truss is determinate, indeterminate, or unstable, I'd go through here and count the joints. In terms of joints, my joints are red. I have 1, 2, 3, 4, 5. So J equals 5. I'd count the members. I have 1, 2, 3, 4, 5, 6, 7 members. And I have a pin and a roller. A pin has a force in the X and a force in the Y, and a roller has a force in the Y. So I have 3 reactions. If I do my equation, I say I is equal to 7 plus 3 minus 2 times 5. 7 plus 3 is 10. 2 times 5 is 10. I equals 0. This is a determinate structure. If I were to have loads put upon this, I would be able to solve it. Now, that equation is a rule of thumb. It can easily be tricked. So if you look, what I've done here is I've just taken that roller and put it to the side. So if we look how the reaction forces align here, we have 1 in the Y and 2 in the X. Basically, what you've done here is create something that will behave like a compass, and it can rotate in a circle. This support reaction is unstable. But if you did I equals m plus r minus 2j for this, it would equal 0. And you say, well, it's determinate, but it's not determinate because of the way the forces are. You have 2 concurrent forces. This force here and this force here act in the same direction. This is unstable. Likewise, this truss down here is unstable. Right now, we have 3 vertical reactions. It's basically a skateboard. I can push on this truss and it's going to roll away. So these 2 here are known as externally unstable because of their supports. This final truss down in the corner is internally unstable. It's internally unstable because basically, if you took this right-hand side and moved it up, the members in the middle would just shift up without any resistance. It can shear along this plane. So we can call this a shear panel. Now, this is a little complicated, but the key to taking care of this is basically, if you have a truss and you don't see triangles, you have a problem. So you have a triangle here, you have a triangle here, you have 3 triangles here, and here you have a rectangle. You have a problem. Take, for example, well, you need to have closed triangles. We could also have an issue that if we added an element here and we erased that member there, this would then not be able to resist moment there. When you're looking at a truss, if you don't see closed triangles, you're going to have an internally unstable truss. So this truss I have up here right now is internally unstable. So I would encourage you, use I equals m plus r minus 2j as a preliminary thing, but you also need to look and think about all the things you're going to analyze before you get into it. If it looks like a skateboard, it is a skateboard, and it's not going to be a useful truss. If it looks like it's missing elements, it's not going to be a useful truss.